Okay, let's get started. Welcome to the online Spintronics seminar number 88. Thank you for joining us. Our speaker today is Dr. Jakub Železný from Institute of Physics of the Czech Academy of Sciences. His talk will be about spin transfer torque and non-collinear antiferromagnetic junctions. Dr. Železný got his PhD in Prague under Thomas Jungrith. And then he was a postdoc in Dresden at Max Planck Institute for Chemical Physics of Solids, where he worked with Claudia Felser. And now he is a group leader at the Department of Spintronics and Nanoelectronics at the Institute of Physics in Prague. So with this, I'll give it over to you. Jakub, please go ahead.
Okay, thank you. And I would like to also thank you and Shin for inviting me to this nice seminar. So I will talk today about the calculations we have done in the past year or two on mainly spin transfer torque in antiferromagnetic junctions. So just at the beginning, I would like to just mention some of the people who contributed that. So the main work was done by Sri Krishna Ghosh, who was a postdoc in our group also, and we done this also with Aurelia and Manchon. But there were also a lot of other people contributing, especially people from to various aspects of this work, especially people from Claudia Felser's group, Jairo in Mainz and Libor, Rafael, so quite a few people, also experimentalists, but I will be talking mainly about theory today because I'm a theoretician. So I want to be talking about antiferromagnetic junctions. So at the beginning, I want to explain what that is. So as you all know, in kind of the basic Spintronics device, to me at least, is the ferromagnetic tunneling junction or spin valve, which are these devices where we have two ferromagnetic layers separated by a narrow spacer. And these can be metallic or tunneling. And what I will be talking about today are analogous devices made out of not ferromagnets, but non-collinear antiferromagnets. And I will explain why we do that, why we think it's interesting. And I will show calculations showing how these work and showing that these do indeed work in ways that are quite comparable to the ferromagnetic ones. So in the ferromagnetic junctions or spin valves, kind of the basic effect is the giant magnetoresistance, which is the difference in resistance between a junction which is parallel, so when both of the layers are magnetized in the same direction, and a junction which is antiparallel. And kind of on the most basic level, the way we can understand this effect is as an analog of having two optical polarizers as shown here. So in a ferromagnet, we have a spin-polarized current. And so we can imagine that if in a parallel junction, the spin-polarized current can freely flow through, in an antiparallel junction, it cannot. And so we have a difference in resistance. This magnetoresistance effects can, of course, be more complex. It's not just related to the spin-polarized current, but it does play a role there. And as I will explain in what we do, it is a key ingredient, the spin-polarized current. And so, of course, the magnetoresistance is used in magnetic sensors. It's very useful technology. But there is another effect, which is the spin transfer torque. And so when we have now the two magnetic layers magnetized along non-parallel directions, the spin-polarized current has to reorient as it enters the second magnetic layer. And so when it reorients, that means there is a torque on the spin current, but that means also there must be an opposite torque, which the spin current exerts on the magnetization. And so this is the spin transfer torque, and this can now be used to switch the junction between parallel and antiparallel states. And this you can use, for example, for the magnetic random access memories, where these junctions are the basic building blocks. And so these two are, I would say, the key functionality. So we can electrically, using current, switch the junction between two stable states, and we can electrically then detect these two states. Now, people, we are interested in antiferromagnets, and there's quite a few reasons why, but I would say ultimately that the point is that we believe there might be some advantages of antiferromagnet over ferromagnets for spintronics specifically. And I would say maybe the most kind of obvious reason is that the dynamics in antiferromagnets is very fast. And I will show some results on that. This in practice means we can do the switching 2 or 3 orders of magnitudes faster than ferromagnets. So it's a really big difference. Another reason is that there are no stray fields, which in something like a tunneling junction is definitely an advantage because this is not something you want. And ultimately, I would say maybe the most interesting aspect is that there is a huge variety of antiferromagnetic materials, and I would say also of both magnetic orders, but also of different material types. So there's lots of semiconductors, for example, antiferromagnetic, which you don't have so much with ferromagnets. And if you look, there is a nice database of kind of more complex magnetic materials called Magnedata. If you go there, vast majority of materials there are antiferromagnets. So it really seems that if you go beyond like very simple magnetic orders, antiferromagnetism is very common. So to me, that's also another reason why to look into those, because they are actually very common magnetic order in nature. Now, people have quite early after the discovery of the spin transfer torque in ferromagnets, people have looked into the analogous effects in antiferromagnets. I'm giving here 2 papers. This was the first one. This one I give here as an illustration of calculation, which involves kind of chemically accurate junction. There are much more references than this. We summarize some of those in this review paper. And they do find large effects. So there is some magnetoresistance in these devices. Theoretically, they do find large effects. So there is large magnetoresistance, large spin transfer torque. But also emerged fairly soon is that these effects appear to be very sensitive to disorder in a way that does not exist in ferromagnets. And so this is a calculation from this paper, which shows that in antiferromagnetic junctions, you basically only have a torque if you have large mean free path. So here, basically, this means you have much larger mean free path than the size of your junction. Whereas so these lines you see here drop very quickly. Whereas in ferromagnets, you don't see anything, and you would not expect to see much difference because the spin-polarized current will be there even if you have significant disorder. And in fact, this paper even shows that in the semi-classical limit, in these simple antiferromagnets, you don't have a torque. And the reason, and I'm going to talk about this more, is actually most likely that in these antiferromagnets that people have to look at, you don't have a spin-polarized current. So they are very different from ferromagnets in this regard. And at least for the spin transfer torque, that seems to be a major problem. Experimentally, this was not observed, and I think this was the main reason why people have, I think, largely moved away from this direction of research. What I also want to say is that even in the very simple antiferromagnets, it's still not something fully understood. It's clear that the effects in principle can exist. There's also some predictions that in a tunneling devices, they may be more robust. So it's something that's not really understood. Nevertheless, people have moved to different types of effects, which I will not summarize here because antiferromagnetic spintronics as a whole is a very large field now. But most of these effects are based on spin orbit coupling. So these are relativistic effects in contrast to the spin transfer torque or giant magnetoresistance, which are non-relativistic effects. And so I give here just one example of the Nell spin orbit torque, which was something we predicted, was then experimentally observed in this copper manganese arsenide. And it's still something that's very actively studied, and it's definitely a very interesting direction of research. But I still think it would be very interesting if we could kind of go back to the basics, and if we could do with the antiferromagnets, what to me is the most basic spintronics device, which is the junction. Now, as I've said, we don't have in the simple antiferromagnet spin-polarized current, and that's kind of, I think, intuitive to understand. We simply, the spin currents from the 2 sublattices will cancel out. Now, the reason, if you kind of start looking into why that is, the reason is symmetry. And so if you look at some very simple antiferromagnet like this, for example, this breaks time reversal symmetry. And so this means if under time reversal operation, my magnetic moments will flip sign because that's what time reversal does. But you see now that these 2 states, this one and this one, they actually differ only by translation. So this means in a simple antiferromagnet like this, time reversal is broken, but in a very specific way. And this means the time reversal plus translation is a symmetry. And this means there will be no spin-polarized current. Or if we look at something like copper manganese arsenide, the structure is a bit more complex, but we find something similar. We find that if we do inversions, we have inversion center here. If we do inversion, this sublattices will switch. Then if we do time reversal, we will now have symmetry again. And this will again prevent the spin-polarized current. But the good news is this is not some fundamental property of antiferromagnets. If we go to more complex antiferromagnets, we can have systems where these symmetries are broken. And we first looked into this in these non-collinear systems. So these are antiferromagnets of manganese 3X type, and they have this triangular magnetic core. And the key thing here is that they are non-collinear. And now these symmetries will be broken because if you imagine, for example, if you do translation from this atom to this one, the atoms are not just reversed, they are somehow rotated. So I cannot do just time reversal plus translation, and the same thing with inversion. They are still antiferromagnets in the sense that in the, let's say, in the non-relativistic limit, the magnetic moment is zero by symmetry. With spin-orbit coupling, they do have small moments, but people still do call them antiferromagnets, which I think makes good sense. And this also depends on the direction of magnetic core. You can also have no moment even with spin-orbit coupling in some cases. Because these symmetries are broken, we will have a spin-polarized current, and I will show why. We will also have other effects that normally you would not have in antiferromagnets. So, for example, this anomalous Hall effect. There has been also loads of work on this. I cannot give here all the citations. Just give here the first one where this was predicted theoretically for the anomalous Hall effect. And this is where we predict the spin-polarized current. So I'll try to give you some basic idea how we can get a spin-polarized current in an antiferromagnet, because I think it's not intuitive, and it wasn't intuitive to us when we first did that. So the basic idea is, in the non-collinear antiferromagnet, if you look at the Fermi surface, so this green circle denotes some kind of simplified Fermi surface in this kind of material, and here the blue arrows denote the spins of the electrons, and the gray arrow denotes the velocities. Now this is in equilibrium. Now if we apply electric field, what will happen is there will be a redistribution of electrons. So we will now have more electrons that move along the electric field than against the electric field, which means now we have a net current. But now if we will look at the spins of the electrons, these electrons that carry the current will actually also have some net spin, which is kind of hard to see from this picture still. But if we simplify this even further, just say, okay, we only have 3 electron types, you can kind of see this from here with the redistribution that this will no longer cancel each other, because these spins that are along the electric field, there will be more of those than these, and this will not cancel out. So there will be a net spin of the conduction electrons. What's also interesting, and this I will not really talk about today because I don't have time for that, the same mechanism also gives you a transverse spin current, and this is what people now sometimes call a magnetic spin Hall effect. And this you can also see here. So you have, this spin up electrons, they move dominantly down, these move dominantly up. So then you have a transverse spin current. And this is similar to the spin Hall effect, but the origin is distinct, and the origin is magnetic, which makes it very interesting from some point of view. We did calculations of the spin-polarized current in these materials. I don't really want to go into details. The key point here is that these are the spin polarizations of the current. This is basically the spin current divided by the charge current. You see those are not huge, but not really negligible. There are also large transverse currents, but those are not so important here. What we show here is the dependence on the gamma, which here is the parameter describes disorder. What this means is this is something which is this is logarithmic plot. So you see this is something that's strongly sensitive to disorder. This is exactly the same as for normal conductivity. So this is really something where it's a spin polarization of the charge current, and it behaves very similarly to charge current. What's also important is that the origin is really quite similar to the ferromagnets, although there are key differences. In particular, in ferromagnets, you have the 2-current model, so you can separate spin up and spin down currents approximately. We cannot do that here because simply spin is never a good quantum number, and you can clearly see that here. We cannot talk about 2 currents here. But otherwise, it's quite similar. It's also non-relativistic in origin. We also see that the effect of spin-orbit coupling is not large. I will be talking about the non-collinear antiferromagnets now, but actually a lot of this will also apply to collinear antiferromagnets. We now also have examples where you have a spin-polarized current also in collinear antiferromagnets. One example is this ruthenium dioxide, where again we will have all the necessary symmetries broken. We now break that because this is kind of a top-down view of the antiferromagnet. What breaks the symmetries here is the combination of the collinear magnetic or with these non-magnetic oxygen atoms. You see kind of the environments of the spin-up and spin-down sublattices are anisotropic, and this is what now breaks the symmetry, because if I do translation, well, I cannot do translation, right, because the environment is different. This now is interesting in that now we actually do have a two-current model, and what we especially we have this paper about this where we discuss mainly transverse currents, because now what's exciting about this is we can have a transverse spin current, so we can do a spin charge conversion in a spin conserving system, which we call a spin splitter in this case, because of this kind of spin conserving nature. But we did these calculations so far only for non-collinear antiferromagnets, because this is what we have realized first, and we haven't got to doing this for the collinear systems. Now, so I'll be showing numerical calculations. We have done this using Quant, which is a very nice package for doing scattering calculations. We use fairly simple model, and we use simple model because from kind of previous literature, it's clear that what's really important here is disorder. And it's clear that if we do a perfect junction, we will always find some torque, we will always find magnetoresistance. But what really should make these materials special is that these effects should be robust. So what we have to look at is disorder, and we wanted to look in particular also at kind of interfacial disorder or structural disorder, which is very hard to do with realistic electronic structures. So we use quite simple model. We use this Kagome lattice, so we do a 2D model, which is, again, only reason is to make it numerically more feasible. This has 3 atoms in its cell, which is tabulated to make it rectangular, so that just we create the device more easily. And the model is simply, we just have S electrons, and we couple them to some local magnetic moments. We have no spin-orbit coupling in the system, so we do everything in the non-relativistic limit, just because we want to see the analogy of the ferromagnetic effects, which are non-relativistic. We also see that in the real materials, the spin-polarized currents are not actually very sensitive to the spin-orbit coupling. So we think this should be actually fairly reasonable to neglect it. So the system we use is set up like this. So we have 2 magnetic layers with this triangular magnetic order. We use a system which is finite along the y direction, but it's very wide because that's more realistic. But we make it finite mainly for technical reasons and because we want to have the interfacial disorder. And then we attach a semi-infinite lead. So the leads are semi-infinite. So the left lead would be semi-infinite in this direction, the right lead in the other direction, and they are perfectly periodic. And so the transport is then calculated by basically matching the incoming wave functions with the outcoming wave functions. It's basically a scattering problem. And then this area is the scattering region where we can add the disorder. And when we add disorder, what we do is we average out our lot of calculations so that we get some reasonable results. Now we have 2 types of disorder. One is random on-site energies. So this is on-site disorder, which simulates something like an alloy disorder or even maybe phonons. So it's simple models, so it's, it can mean a lot of things. And we do that. We just use a Gaussian distribution and choose randomly the on-site energies using some standard deviation, which is this parameter d. And then we also do interfacial disorder, and this is really something that's not normally done in these calculations. And we wanted to really do this because experimentally it is always present. There are always steps on the interface. I give here an example of how it looks in our case, just a part of the junction, because the junction is actually very wide. And you see, in this case, there will be quite a lot of steps, so very rough interface, which I think is quite realistic. I mean, I'm sure maybe it can be in some cases better, But I think this is actually much more realistic than assuming a perfect interface or a perfect interface with one step. So we wanted to do that. Now, I just want to briefly comment on how we actually calculate the torque. In general, the torque is connected to the current induced spin. So this is something that holds even with spin orbit coupling. It can be shown kind of generally. So the torque on some site or on a magnetic site will be given by a spin induced by the current on this side. Because we are in the non-relativistic limit, it's also true that the torque is directly given by the spin source. So the spin current sources, yeah. So this is a spin current. If we take, so the gradient of this will then give you a source of the spin. And so this means you have two ways how you can calculate it, which doesn't really matter from practical point of view, but in terms of kind of understanding what's going on, this is crucial. It also means that spin current is, in this case, actually well defined. And this is, I think, quite important because normally with spin currents, there are a lot of issues on how to define it. In this case, I think it's fine, even though spin is not conserved for the conduction electrons. Spin of the whole system is conserved, and we can clearly define it. And so we can calculate then the torque by either calculating the spin polarization or looking at the spin current that flows in and that flows out, and then the difference will basically give you the torque. And this also means that automatically the torque has to be, in this case, connected to spin currents. So we did everything also for ferromagnets, ferromagnetic junction, just for comparison. And so I first start with the ferromagnetic junction, where we find something which is well known, but just to kind of set the stage. So what I'm showing here is results for 3 different configurations of the junction. So this is parallel, perpendicular, antiparallel. And here I show the spin currents throughout the junction and the torque as a function of the x coordinate, and we kind of integrate everything else. We integrate our y and the unit cells. And what you see is kind of straightforward, I would say. In the parallel junction, there is a spin current going through, but it's constant. There are no spin sources, so there is also no torque. This is how it has to be, because here everything is collinear. Spin must be conserved, so there can be no torque, but there is still y-polarized spin current. In the perpendicular, now there will be a torque, so we have an incoming y-polarized spin currents, which gets very quickly absorbed, but then we will have an x-polarized spin current coming from the right magnetic layer, which will also be carried by the reflected electrons back into the left layer, and so we have torques in the both that are kind of equal in magnitude, but at different directions. And then in the antiparallel, we have again no torque. So this is well known. And then if we want to understand how the torque depends on the rotations, here I give the full dependence on when we rotate the magnetic order of the right magnetic layer. This is the torque in the right magnetic layer. I'm sorry, I'm missing here the label space X, Y, and Z components of the torque. We can understand this actually very easily. So I said the torque is given by the absorbed spin current. The absorbed spin current is polarized along the left magnetic layer. But in a ferromagnet, the component of the spin current, which is parallel with the magnetization, will not get absorbed very efficiently, only the perpendicular component. So this means what we have is the spin current minus the parallel component. And this is equal to this expression, and this is a well-known anti-damping torque. This is called anti-damping because it has the same formula as the damping torque term in the dynamic equations for the magnetic moments. And this really, now here the blue line is a fit to this. You see it's not perfect, but it's quite good. So this kind of behaves in an expected way. We also see some Z component of the torque, which is now a field-like torque. This happens because the absorption of the current is not perfect, and the electrons that reflect, if kind of the magnetization is misaligned, they will have a component which is along the Z direction, so there will be a Z current. And so we get also that, but we generally see, and this I think is something this is well known, is with this order, this Z torque tends to be quite small, whereas this one is much more robust. And so this is quite well known and can be understood on very simple arguments, which is nice compared to spin orbit toric, where things are much more complicated because then spin is not conserved. Now, if you look now at the antiferromagnetic junction, what we see is quite different. So first, what I'm showing here is a case where we remove actually the other magnetic layer. So we just have a non-magnetic layer and then one magnetic layer. And you still see there's still a torque, and there's still an absorption of the spin current. And this is very different from the ferromagnets, where it's not possible in the non-relativistic limit again. And the reason is that we now have a non-collinear antiferromagnet, and now spin is never conserved. And so when spin is not conserved, we can have a torque. And so you see that what happens here basically is that incoming electrons get polarized by this layer, but so it creates a spin current, but this spin current can get partially absorbed in the layer itself. And so then this creates a torque, which is now a very different torque than in ferromagnets. It's now a self-induced torque. Now, if you look at the parallel cases and the antiparallel cases, we now see there's still a torque where there couldn't be in the ferromagnets. And this again is because now spin is never conserved. And so now we see a torque in all these cases. So this is a key difference, which I think in practical terms is quite important, because this fact that you don't have a torque for the parallel and antipolar states, it's actually a problem, because those are the stable states of the junction. So this means you need some thermal fluctuations for the switching, which makes the switching slower, and it also makes it stochastic to some extent. Also, what I want to mention here is that for this configuration, the spin current that flows here is always polarized along the C sublattice, which is not because the sublattice would be somehow special, but it's because by symmetry, it has to be polarized for this configuration along the y direction. And then if you rotate the magnetic order, because we don't have spin orbit coupling, the polarization has to rotate the same way. So then it will always be polarized along the C direction. Now we can actually understand the torque still on some very simple arguments similar to those in ferromagnets. So we have two spin currents here, the left and right spin polarized currents. The left spin polarized, and then we look at the right magnetic layer. So the left spin polarized current will enter the right magnetic layer, gets absorbed. So on each sublattice, we again will have dominantly the perpendicular component to that sublattice will get absorbed. So we'll have a anti-damping torque similar to that in ferromagnets, but now on each sublattice will be different. And that's, of course, a huge difference then for the dynamics. But it's still somehow similar to the ferromagnetic case. But now in the right magnetic layer, also the spin polarized current from the right magnetic layer will also get absorbed. So now we'll have this expression, which differ only by the fact that here, this is the polarization from the left layer, whereas this is from the right. So they look quite similar, but will be very different in practice, because here, this depends only on the magnetic moments within the system itself. So it's clearly it's internally generated and quite different. When we look at the calculations on each sublattice, you really see that we can fit this reasonably well. So here, this dotted line is the anti-damping torque, the dashed line is the self-induced local torque, and the solid blue line is the total line. You see, it's not perfect fit, but it reasonably explains the calculations. And we again see a Z component as well. I don't want to discuss it too much. Just one thing I want to mention here, which I think is possibly interesting, is that we actually see very large torque on the sublattices, which cancels out. So the total is quite small, but the sublattices on A and B, we see large torque. We do not think this actually will play a role for the dynamics, probably, because for dynamics, mainly the total should play a role. But nevertheless, it's a feature that we can always see for various parameters and don't really understand, I think, at this point. And it comes from local spin current. So it's still connected to spin current, has to be, but not to this global spin polarized current, but it comes from a local spin current. Now, this self-induced torque, I just want to mention a little bit why we think it's quite interesting. So the difference compared to kind of the normal spin transfer torque is that it does not come from the other layer. It's internally generated, so self-induced. And so it's quite similar to the spin orbit torque in that it's also a self-induced torque and local torque, but it's non-relativistic. So, it doesn't come from spin orbit coupling. So obviously it's distinct from the spin orbit torque. One thing I also want to mention is that because our system actually does not break inversion symmetry in the bulk, we only will see it close to the interface. We need the interface to break the inversion symmetry because the inversion symmetry is needed to have any torque in the linear response regime. But if we would have a material that breaks the inversion symmetry in the bulk, and we have some examples, actually some preliminary calculations, you would see a torque like this in the bulk, and then you really have something analogous to the spin orbit torque, but non-relativistic in origin. What's also clear about this torque, and this makes it quite special, is that because it's self-induced and non-relativistic, what this means is that if you rotate the magnetic order, the torque has to rotate with it because there is kind of no reference to it. So I just show this here as an example of how it will look if you rotate 90 degrees, torque will rotate with it. And what this means is that it's quite hard probably with this torque to do some deterministic switching between two stable states because the torque will never vanish, it will always be there. So I think it will tend to lead to something like persistent oscillations, and I will show some basic dynamic simulations. Now, the main motivation of these calculations was actually to look at the disorder dependence, and so I will show this here in a few slides. So what I'm showing here is a comparison of this is the angular dependence. So when we rotate the right magnetic layer, these are the X, Y, and Z components of the torque, and what I'm just showing here is that the angular dependence is not really changed by disorder. The magnitude is, but that's expected because also the conductance will become lower. And here I just changed the on-site disorder. We used 25 steps from the interface, which is already quite significant disorder. Here what I'm showing is the same plot, but now with a different number of steps. So this is with perfect interfaces, and this is now with 25 and 100 steps on average. What you see is that there is, in magnitude, it changes quite a lot between 0 and 25, but then it doesn't really change much anymore. And this suggests there is some interfacial contribution, which is sensitive to having good interfaces, but actually there is also a large contribution, which is not sensitive to that and which will be robust. And this to me is a very important result because it's not maybe that obvious that in an antiferromagnet, it wouldn't really matter where your interfaces end because then it depends which spins will be the last. So it really shows this effect which somehow originates from the bulk. These plots show kind of the overall magnitude of the torque as a function of the on-site disorder and for different numbers of steps. For the ferromagnet, these are two values of the Fermi level. So, it's a toy model, we can put Fermi level where we want. So we use different values of Fermi level just to see that what we see is somehow like general behavior, not some random property of one set of parameters. And we compare antiferromagnet and ferromagnet. I don't really want to go into detail of this. What you see is that the disorder does certainly matter, especially the interfacial disorder, but the torque is relatively robust and comparable in the antiferromagnet to the ferromagnets, also in terms of magnitude. So here the magnitude is scaled by the conductance, which is probably the useful quantity for experiments. And to me, this really suggests that what we see should be fairly robust. And we see in agreement with kind of the ferromagnets, we see that the Z component is more sensitive to disorder, and the in-plane component, which would be described by this anti-damping and self-induced torques, that will be more robust. We also did magnetoresistance calculations. We haven't really studied those systematically, so I'll just show this with just one slide. But basically what we find is that, again, it's quite similar to the ferromagnets. You see that it decreases quite strongly with disorder, which is expected for magnetoresistance. See, these values are huge because we have metallic junctions. We would certainly not expect 1000% GMR. So this is of course unrealistic. But what we see is, again, that it survives even quite significant disorder and is comparable to the ferromagnets. So we believe kind of the basic functionality should be there. And then, so we have the torque calculated. So what we also wanted to show is that this torque can actually be used to switch the junction, because that's the main functionality we actually need. So here we did using this in-plane component. So we take the anti-damping torque, the in-plane torque, we take parameters as it is calculated, the magnitudes. And what we show here is in these top plots, it's a switching from parallel to anti-parallel junction. So we have one layer which is basically assumed is fixed, and switch the right magnetic layer by 108 degrees to go from parallel to anti-parallel. We use current pulses with opposite polarities. And we showed that you can switch deterministically, you can switch very fast. You see here these very fast oscillations within the XZ plane, I think. Those depend a lot on the parameters. So if you would have large damping, it would oscillate much less. But nevertheless, the switching still is very fast. You see it switches completely within 40 picoseconds. You have in ferromagnets typically something like nanoseconds. I think going beyond hundreds of picoseconds in ferromagnets would be very, very difficult. So I have something that's quite fast, and which is importantly, it's deterministic switching. It doesn't depend on timing of the pulse or things like that. Now, here, as I said before, this self-induced torque, we don't think can do switching by itself. It will just do oscillations, and then it will be very hard to actually deterministically switch between two stable states. But what you see is that and the anti-damping torque can do it by itself. You don't need the self-induced torque necessarily. But we also see that the self-induced torque can reduce the anti-damping torque that you need for switching. But also the relation between the two is quite complex. I think this is something that we would like to explore more, because it's quite different from what exists in ferromagnets or collinear antiferromagnets, where we have some experience with it. So I think this is potentially quite interesting, especially I think for not just for the torques, but also for some oscillators. So you could do some terahertz oscillators with this. We also use the TZ torque for switching. You can see the switching here is even faster. You have like 4 picoseconds. The exact times will depend a lot on the individual parameters, but you can generally expect something like this in antiferromagnets on a picosecond timescale. Just very quickly before I finish, I will just show last few slides. So in everything I've shown, what we have used is the leads, which we have are magnetic, or have the same magnetic order as these regions. So this means we have actually semi-infinite magnetic regions, so very corresponding physically to very thick magnetic layers, which we use mainly because it's just the simplest case. It's not very realistic, of course, because normally you would have very thin layers. What we also have done, and we have done this systematically, is also using non-magnetic leads. Then we have very narrow magnetic layers. What we find is that in ferromagnets, this doesn't matter basically at all. You find even quantitatively, the results don't really change much. In the antiferromagnets, they do change a lot. And this is probably because we now introduce another interface, and we have a torque, the self-induced torque originates from the broken version symmetry interface. So it makes things more complicated. But importantly, I think qualitatively, the conclusions are similar. So I just don't want to go through this in detail, but this is a comparison between the magnetic, non-magnetic leads. You see for the non-magnetic leads, the angular dependence is very different. And the fitting by the anti-damping and self-induced torques is worse. It's much worse, but it's all the physics is still there. It's just clearly it becomes more complicated. If we look at the magnitudes, again, we see quantitatively it changes, but qualitatively not so much. Whereas in ferromagnets, you see it's almost the same. I mean, there the plots really do not change. In the antiferromagnets, they do change a lot, but qualitatively, the results are very comparable. So we believe that what we propose would be realistic. Even in narrow magnetic layers, these effects will exist. They don't need really thick layers. So that was all I wanted to show. I would say the main message for me is that we really see something that could maybe be expected, but I still think it's good to show this explicitly, that the spin-polarized current really does lead to a robust spin transfer torque in these devices. And that not only survives normal disorder, but also this interfacial disorder that's really inevitable, I think, experimentally. we also see this for the magnetoresistance that we haven't really tried to understand in detail, but again, I think it's reasonable to expect that it will be there and will be robust. But we also see there are new features that you would not have in the ferromagnetic junctions, which are, I think, not really specific to antiferromagnets, but really originate from the non-collinear order. So any non-collinear magnetic material you would see similar things. In particular, we see the self-induced torque, which will change things a lot. I think it opens up new possibilities. We see that the torque always is present for any configuration, even for the parallel and antiparallel, which again makes the switching easier, makes it less stochastic because the torque is immediately active as soon as you have the current. It is active, whereas in ferromagnets, you need the thermal fluctuation and they have a very small torque. So the switching starts very slowly and only becomes fast when you have significant deviation. And whereas here we really do see a switching which is fast and which is deterministic. So I think it has all the functionalities for the experiment. I think it can offer really some advantages like the speed, which might be hard to use in practice in the end because it's really very fast. So electrically, maybe getting down to picosecond range is hard, but nevertheless, the speed is in principle there. Maybe it's also interesting for the oscillators. You can get to the terahertz regime very easily. And opens up, I think, much more materials you could do these devices with. And these results, most of what I've shown is from this paper, which is an archive and published it. Okay, thank you for your attention, and I'm happy to answer questions.
Okay, thank you very much for this interesting talk. We can use the reactions buttons to thank the speaker. If you have a question in Zoom, please use the raise hand feature. If you're watching on Twitch, just type your question in the chat box and I'll read it for you. Okay, so I don't see questions so far, so let me...
He has a question in the chat box.
John, please go ahead. John Shao.
Okay. Thanks for a nice talk. Yeah, can you go back to that slide you showed the spin? I think a spin conductivity comparison between the manganese tin and manganese iridium.
Sure. Yeah.
Spin hole conductivity you calculate. Yeah.
Yeah. You mean this slide?
Yes. And I just try to understand the notation. So the superscript means the spin polarization. So
yeah. I didn't hear. I mean, are you asking about this?
I'm looking for this picture. The picture you show. This is three curves. So for the manganese 310, and you have a sigma x y x, right?
Yeah.
I just want to understand the notation. Notation that
you mean of this tensor?
Yes.
Yeah. Yes. Okay. Here, what this means is the top index is the spin polarization of the spin current, and then in the bottom, the right index is the electric field component,
right,
and the left index is the direction of the spin current flow.
Right. So in this case, you do not see the Z polarization.
The Z polarization is here very small. Yeah.
Very small, but X polarization is much bigger.
Yeah. Honestly, we've done this years ago, so I now don't remember exactly, but I think this is quite general feature of these.
But if you turn on the spin opto coupling, then I will expect the Z component becomes big. Is that?
Well, here actually we also have calculation without spin orbit coupling. It's just very. I think here the solid lines are with spin orbit coupling, and then there are dashed lines behind which you can't see because they are exactly behind the curves which are without spin orbit coupling. This is not something we understand fully. I mean, it's a bit surprising why in manganese 310 the spin orbit coupling has basically no effect, but it's really something that we see. In manganese 3 iridium, if you look there, it has a bigger effect, but still, I'm not sure if you would have the Z component, actually. I would have to look precisely at the symmetry of these tensors too, but in principle, they can be there.
Jakub, I think we lost your audio for the last maybe 30 seconds.
No.
Is it
was continuous? It was continuous.
Okay, sorry. Must be on my side then.
Yeah, okay, thanks.
Okay, Feisho, next question, please.
Hi, thank you for the next talk. So I wonder about this relation. You mentioned that the self-induced torque can assist or help the switching, but I wonder whether it can also hinder the switching. If somehow we can numerically, change the relative sign between this self-induced torque and the spin transfer torque, or maybe this is there's no generalized way to simplify everything into feel like damping light term, maybe higher order is also not possible.
So we've tried done this kind of just to illustrate it's possible. I've tried to play with this a little bit, and so it seems it definitely can hinder the switching as well. I think what it looked like for these parameters was that actually for switching from the parallel to antiparallel, it helps, and then for the other one, it hinders.
I see.
But this may be very dependent on the parameters. I tried a little bit to kind of find a set of parameters where it helps in both, and I wasn't successful. But I think these things would really have to be done systematically. So it can definitely do both. But yeah, it's very. It also really seemed that there is kind of very non-trivial relationship between the two. Or kind of it behaved in a bit strange way, like you increase the torque and then now suddenly it behaves differently. So I think there is probably work to be done in understanding how these work, but they definitely work very differently. I mean, the formula is similar, but they are not actually very similar. The self-induced is not anti-damping like at all, I think. It's not field like either, but I don't think it is anti-damping like.
But do you know kind of the order depend on the magnetization? It's like maybe higher order.
I mean, if you look at the formulas, I'm not sure if you, I don't know if you can say it's higher order necessarily, right? I mean, in a sense, maybe yes, because this has three magnetic moments. The self-induced has three magnetic moments. The anti-damping has two because this ML is just external. Right. So in the sense, maybe yes.
I think Kirio's paper has a systematic way to actually analyze all kind of higher order into the spherical harmonics. So maybe this is another type of interesting spherical harmonics we always ignore.
I think so. I mean, I've tried a little bit to look at the symmetry, and then I realized I would need, I guess, some formalism, because we do this quite a lot, this kind of expansion of the torques in the magnetic order, but we do this in collinear systems where it's easy because you have one order parameter. And then I realized, okay, I don't actually know how to do it here, or not in kind of straightforward ways. So we haven't done that yet, but it would definitely be good to do it and to kind of then systematically do the dynamics. I think it's interesting. I think because it will be different from ferromagnets, and kind of there's more complexity there.
Yeah. Okay. Thank you so much. Very nice talk.
Thank you. Hui Chen, you're next, please.
Thanks for the nice talk, Jacob. I just have a question on the effect of band structure in these simulations in general. Do you have flat bands for this particular model? And if you choose a chemical potential that specifically is aligned with the flat bands, do you have stronger effects?
I didn't understand precisely what you're asking. Are you asking about the what would happen if the band structure was more realistic?
I guess if you just consider the Kalumi model, there will be with nearest.
We use actually your model. I mean, the model is exactly including the parameters. It's exactly, I think, taken from your paper, except we don't have the spin orbit coupling.
I got that, but then there should be a flat band.
The flat band. Yeah, I guess we just away from the flat band. Yeah, that band is not. That's. So I'm not sure if we get it, but I guess we do have it. We just put the Fermi level somewhere away from that because I guess that's not very realistic. That would give you, I think, strange results.
Yeah, I guess it would be interesting to see how the density of states and Fermi energy can affect.
Yeah, sure. I think you would get some strange things, but I'm not sure if it's realistic. I mean, I don't know, but I would think this. I always saw this flat band as just kind of consequence of the model being too simple. Kind of, we're missing something, so then the model is a bit unrealistic in this regard.
Yeah, the thing is, if you have a coupling structure with dominant nearest neighbor hopping, then there must be a flat band somewhere.
Okay.
Sometimes.
But I mean, in the DFT systems, we don't see that, right? I mean, we don't see. I think I don't remember. I don't remember we saw any flat bands there. So for us, we really. I mean, I like these models a lot. We use them actually quite a lot. But to me, it's mainly to understand kind of these general things. But I also think it would be much better, of course, to use realistic electronic structure.
No, I mean,
that's very hard to do. So
just want to get some more features out of your simulation results. Anyway, thanks a lot.
Yeah, sure, no problem.
Thank you. A quick question from chat. Are you using Quant or T-Quant?
We use Quant, yeah. This was even before T-Quant, I think, was a thing.
Yeah. Okay. Are there any other questions? So let me ask you, so in this self-torque discussion, so since you have a self-torque, I suppose that means that there is a spin current that is going away from the interface.
Sure, yeah.
Right? Is it possible to introduce some phenomenological expression that will give the spin polarization of this torque in terms of things like the surface normal, some sort of maybe tensorial representation of the order parameter, but something phenomenological that doesn't include microscopics?
I think so, yeah. I mean, the torque, really what only governs it are the two polarizations of these two, of the left and right spin currents. So the only thing that...
There's no left if it's a self-torque.
Oh yeah, with the self-torque, yeah, sure. This we haven't really thought about. I think this will depend on symmetry of the interface, but I think again maybe not so much because in the non-relativistic limit, there's not so much that can happen.
Yeah, this is what sort of my question comes from, because with the spin orbit torque, you have a vector from E cross Z, for example, which is axial because you can make a cross product. Right? So here, with the non-relativistic case, it's not obvious that you can make a combination like that. So if you can make a combination like that, that's fine. But if not, it might mean that actually full disorder interface would destroy this current.
I think I don't think the disorder would destroy it because it really, all of it is just, and we don't see that it would be destroying it. And but it does behave differently from the spin orbit torque in this regard. It really, I think the direction of the interface, I don't know. I mean, it's hard for me to say now because there are two things that play a role. One is the inversion symmetry breaking where the interface matters. The other is the spin polarization where the interface does not matter. And it's kind of hard now for me to see what would happen when the interface would be along some different direction. I guess the torque would change. But I don't think it is actually sensitive to the interface because, I mean, it is maybe sensitive to the direction, but it's not sensitive to it being nice interface. And we really do see that very clearly. And the reason is that really the only thing that matters is that, you know, as your incoming electrons get polarized, there is no reason why the spin wouldn't get lost, basically. In ferromagnets, there is exact, you know, the spin is not lost. So the amount of spin that gets reflected exactly matches transmitted, so the spin current is constant throughout. And you don't have this here. There's kind of no reason for that here. And to me, at least, that's the most fundamental reason why you would have this torque. I think symmetry, what you're saying is, I think, a matter of symmetry, and we should really do that, but we haven't. We also have calculations. I can't really talk much about those because that's work in progress and it's not work done really by me. But we have an example of a bulk material where we do see similar thing. I mean, we kind of arrived to that from very different direction, but in the end, it's a similar story in that it's a non-relativistic torque. So I think, and self-induced. So I really do believe this is a general thing, and I don't think that it would be destroyed by interface. There's what you say about this vector products. I mean, you can also have, that's what you have for Rashba. If you have a Dresselhaus torque, you don't have anything like that, right? There's no polar vector. You can still have a torque, but yeah, we haven't looked at how precise the symmetry will be.
And with the Rashba, you also have a combination of the.
Yeah, with Rashba you do, but with Dresselhaus you don't, right? With Rashba you need a polar group.
Some sort of tensor, and that describes it. Yeah, so I mean, something to think about. I think the difference from a ferromagnet is because in the ferromagnet there will be a spin current. It's just parallel to the magnetization.
Yeah.
So it's not going to exert any torque. And here it may be different. But the question is whether the invariance between the sublattices is broken enough by the existence of the surface normal, and that should be related to the symmetry.
Yeah, I mean, if we would not do the calculations, I would also be kind of afraid that what you're saying, that kind of it's something that in principle exists, but in practice will get washed out by the sorrow. I really believe it does not, because we really don't see anything like that happening. And we really do see, I mean, you saw that the disorder interface is not small. I mean, we do consider significant. I mean, look at it, disorder is quite rough. I mean, I don't know what would happen. I mean, of course, this is not fully realistic either, because we assume the magnetic order is unchanged. We just replace some magnetic atoms by non-magnetic atoms. That's not fully realistic. But I think it would not matter in the end unless it's something drastic happening, because there is significant disorder, and we still see this torque is not really sensitive to that. So I really believe it is there.
Okay, thank you. Shin, a question?
Yeah, thank you, Jakub, for this very interesting talk. When you described the spin torque caused the switching and everything, it's easy for me to visualize the torque acting on the ferromagnet. But for the non-collinear antiferromagnet, it shows that the torque on each of the sublattices are different. They are even in different directions. So when you do the simulations, do you just use the overall effective magnetic order? Or do you actually basically at these three spins should always keep the 120 degree between them? Yeah,
so we assume a large exchange limit, which means during the dynamics, the angles will not be exactly 120 degrees, but they will be close to that, which is, I think, quite realistic. You will have systems where the exchange is small, but in normal magnetic materials where you have room temperature magnetism, the exchange is huge. It's much larger than any other field you have. And we also assume there's no domains. So it's a macro spin approximation, right? So everywhere it's the same 3 spins, but we, as you say, we take a torque on each spin. That's something you kind of have to do in an antiferromagnet, or there are, I guess, ways how to avoid that, but you have to approach it smart. You cannot just ignore the fact that you have, some order, within the unit cell. So we take torque on each sublattice, and when the magnetic order rotates, we take the torque as it should be when it's rotated, because we calculated the rotation, and we let it evolve. That's basically it. In terms of visualizing, I think it's. I also don't really have that much intuition for this. We spent some time a while ago playing with the collinear antiferromagnets, and we kind of built some intuition. It behaves in ways that are sometimes very non-intuitive because of this large exchange field. So in a ferromagnet, the exchange does not normally come into play unless you have a domain wall, right? But here it always does, because as the magnetic order is turning, so it's behaving basically like a solid body on the first approximation, where you rotate all the spins together. But actually, there's always some small cantings, which is there is a small net moment, and this moment, even if it's small, it's actually important because the exchange is so large. So even small canting gives you large exchange field. And so then what happens with the TZ torque, for example, is so the torque is in the Z direction. So initially, all the spins will cant in the Z direction. So you generate a moment. But then what happens? Because of the exchange field, basically the whole magnetic order starts rotating around the Z direction because of the exchange. And that's very similar to what we saw in the collinear antiferromagnets. So it is quite different, and the exchange does come into play, which is the reason for the speed. This is why we get the very fast dynamics.
You mentioned about the speed. It looks like the dynamics had a frequency on the order of at least 20 gigahertz or even higher.
No, I think it's higher, right? This is
100 gigahertz. Oh, this picosecond. Okay.
Picosecond, yeah.
So if I just
I would say terahertz, right? I mean, these you see these have very fast oscillations. You can't even see them here, and that depends on the parameters, of course. But that's kind of normally. I should say these are basically randomly chosen parameters. Yeah, this is, I mean, in terms of the exchange and isotropy. So sure. The reason why it's a terahertz dynamics because we just choose parameters that correspond to that. But that's normal parameters for antiferromagnets. This is not something crazy. In copper manganese arsenide, we did this and with kind of realistic parameters, and we got similar switching speeds, for example.
I see. If you treat this as a rigid body, this the three spins all keep roughly around 120 degrees. They just rotate. So then this rotation is going against anisotropy, I suppose.
Yeah, sure. So the barrier in this case is definitely given by the anisotropy. In this case, I'm not so sure. It has to be studied systematically, which I haven't done. In the ferromagnets, because of the anti-damping torque, the barrier is the Gilbert damping times the anisotropy. So it's much smaller than the anisotropy normally. There has been work on this in collinear antiferromagnets, but I think in these systems, it's not really known. It's not known what the self-induced torque will be. So this also is something that we should look at really.
Right. I just want to say that if the frequency is on the terahertz, it translates to some kind of effective field that is in play that's on the order of 100 Tesla-ish, if I did my calculation correct. So that's really, really large.
But that happens because you have exchange field, which is even larger than that.
Right.
Thousands of tens of thousands of Tesla. And then you have your normal fields that, your torque or your anisotropy, which will be somewhere around Tesla or less. And then what happens, you take basically a geometrical average of that. SIT is the effective field that kind of controls the dynamics. And so then you arrive at something like this 100 Tesla.
I see. Thank you very much for the explanation.
Yeah, sure.
Okay, thank you very much. I think we're out of questions. So let's thank Dr. Železný again.